Hi, welcome to Chapter 9 and Chapter 12, Molecular Orbital Theory, Overview Part 1, where we're really going to focus on the Chapter 9 part, just talk about molecular orbital theory. So what is molecular orbital theory? Well, remember when we said an electron can behave as a particle or a wave? Well, waves have properties that are used to describe the energy of the electron in a molecule. And sometimes waves can be in phase and add together, and sometimes waves can be out of phase and cancel each other out. And that determines our molecular orbits. So molecular orbits have characteristics like atomic orbitals, where each can have a maximum of 2 electrons. Electrons in the same orbital have opposite spin, and they have a definite energy. And you can visualize the electron density by a contour diagram. They differ from atomic orbitals because they represent the entire molecule, not just a single atom, okay? Single atoms are atomic orbitals, and the entire molecule are your molecular orbitals. Whenever 2 atomic orbitals overlap, 2 molecular orbitals are formed. One bonding and one that we call antibonding. We're going to get into what the difference between bonding and antibonding is in a few minutes. So bonding orbitals are when your 2 waves combined, and antibonding orbitals are when you have a destructive combination of your atomic orbitals. And I'm going to show you a diagram of what that means in a minute. They have a new feature unseen before. A nodal plane occurs where the electron density actually equals 0. So what are the guiding principles for the formations of molecular orbitals? The number of molecular orbitals, and we're going to abbreviate molecular orbitals MO, and atomic orbitals AO. The number of molecular orbitals formed will equal your atomic orbitals. Atomic orbitals combine with atomic orbitals of similar energy. And how well the 2 overlap or combine is proportional to how well they overlap. If they overlap very good, then they're going to combine very good. As the overlap increases, the energy of the bonding molecular orbit is lower. So if you have increased overlap, you have low energy molecular orbit for the bonding, and you have high energy molecular orbit for antibonding. Again, as we said previously, each of your molecular orbits can contain 2 electrons with opposite spins. That's Pauli's exclusion principle. And molecular orbits are of the same energy are filled the same way with Hund's rule, okay? Where you have to have 1 up in each orbital before you can have 1 down. That's Hund's rule, remember? Okay, and also when you fill molecular orbits, you fill low energy first. So here's a visualization, okay? So in molecular theory, we think about the wave nature of the electrons, the wave nature of the electrons. If you have 2 waves that will add together constructively, you'll result in an orbital that is lower in energy, and that's called a bonding molecular orbital. And this right here is your bonding molecular orbital. If you have 2 waves that cancel each other out or interact destructively, you will result in a higher energy antibonding orbital. And this here is your antibonding. Notice this says energy going up, so that antibonding is higher energy than your bonding. Whenever there is a direct overlap of your orbitals, you're going to form a bond and an antibond that are called sigma. Remember when we did Vesper theory and we were overlapping atomic orbitals and we formed sigma bonds? Okay, well, just like that, in molecular orbitals, when you have overlapping molecular orbitals, you're going to form sigma molecular orbitals. The antibonding orbital is designated with a sigma with a star on it. This star means antibonding. And here's an example for hydrogen. Okay, remember your antibonding is a higher energy. Notice it's labeled here. How do we label them? Sigma 1s, sigma 1s star for antibonding. Why 1s? The electrons coming here are from the 1s. This is for the bond between the two hydrogens. Why are antibonding orbitals higher in energy? Well, antibonding orbitals are higher in energy because there is less electron density between the two nuclei. So here's my bonding. And there's a high density of electrons right here. See, the electron density is concentrated between the two nuclei right here. Okay? In my antibonding, what do you notice is in that spot? There's your nodal plane where there is zero probability of having the electron there. So this is zero density, really. So because the electrons are not in between the nuclei here, it takes energy to pull an electron away from the nucleus. So here they're both in the middle of these two nuclei, kind of sharing them. Now they're kind of over here. So this only has this one nuclei. You pulled it away from that one. And over here, too, you pulled it away from that one. That takes energy. So thus, when electrons are in your antibonding orbitals, they're going to spend less time between the two nuclei, which result in a higher energy. So how do we actually figure this stuff out and make diagrams? So this is called a molecular orbital diagram right here. Okay, so your energy diagram or your molecular orbital diagram shows how orbitals from atoms combine to make molecular orbitals. So this here is your atomic orbital. And so is this one. And these orange ones are your molecular orbitals. And this is for hydrogen bonded to hydrogen, or H2. So hydrogen has a 1s electron, so 1s electron, both hydrogens here, okay? These are going to bond, and they're going to overlap, so they're going to make a sigma molecular orbital. So here we have our sigma 1s orbital, and how many electrons are in there? 2. Okay, so you have to fill them using the Aufbau's principle. Low energy first. This is the lowest energy. So you're going to take this electron from this hydrogen and put it here. And then you're going to take this electron from this hydrogen and put it here. Now that this is filled, if we had more electrons, now we would move up to the antibonding level here. Okay? Then from your diagram, you can calculate something called bond order. Your bond order is just 1/2 the number of bonding electrons minus the number of antibonding. So here you have 2 bonding, so it's 1/2, 2 minus, there's 0 in there. So your bond order is 1. If your bond order is greater than 0, then you can form the bond. So the bond order is important. It tells you if the bond will form or not. So let's fill out our molecular orbital diagram for helium-2. So helium-2. So this is what we're trying to figure out, if this bond will form between 2 heliums. So the first thing is to write your helium atoms and then draw the orbital notation for helium. Helium ends in 1s2. So you have your 2 electrons in here. Then you draw your molecular orbital diagram and you start filling it low energy first. So you take this electron and you move it here, and then you take this electron and you move it here. But now you have 2 left, so then you take this electron, move it here, and this electron, move it here. Since you had 4 total electrons, you filled both your bonding and your antibonding. Okay, what is the bond order? Remember, it's 1/2 the number of bonded minus the number of antibonded. So will helium form a diatomic? And the answer is no. No diatomic for helium. And you knew that because we said the noble gases don't form diatomics. So you knew that. But now your bond order kind of shows that. So your molecular orbital diagrams show you more than just your atomic orbitals and your Lewis diagrams. It kind of combines them all. And it all has to do with the wave-like property of the electron. So let's try this for Li2. Okay, so Li2 just means Li bonded to Li. Now, lithium's electron configuration is 1s2, 2s1. So we write lithium over here, and lithium over here, and the 1s's. We fill our molecular orbitals, our sigma 1s, and our antibonding sigma 1s. But now we have this 2s. So we have to write the 2s for lithium, right? And the 2s for this second lithium. They will combine to form a sigma 2s and an antibonding sigma 2s. So then you take 1 from each and you fill it. There's not enough to fill here. Okay, now let's calculate our bond order. So it's equal to 1/2 the number of bonding. So here we have 4 minus antibonding. So this gives us a bond order of 1. So Li will bond to itself. Okay. Now, it says here, notice the core electrons don't play a major role in the bonding. Here are your core electrons. So we could have gotten the same bond order without looking at these, right? So if I just use this, what is the bond order? BO for bond order. It's 1/2 the number of bonding minus 0, and I still get 1. So you could kind of ignore, these are your inner core. You could ignore these and just look at your outer sublevels. Well, what about when we get to the p orbital? Remember, the p orbital has 3 distinct orbitals, your x, your y, and your z, okay? So when you're combining p orbitals, if you happen to be on the internuclear, that's a fancy word, internuclear axis, that just means the axis that the nucleus of your atom is on. If you're on that axis, your 2 p's are going to overlap. So this is called overlap. If your p's overlap, they're going to form a sigma molecular orbit. So overlapping p form sigma molecular orbits. The other ones don't overlap. They will, in the internuclear axis, they're either above it or kind of sideways to it. And those are going to form your pi. These are called sideways overlapping. Sideways overlap. They form pi molecular orbits. So in your p, you're going to have 1 sigma and 2 pi's molecular orbits formed. So how do we draw the molecular diagram when we are putting in the p block? So there are sigma and sigma stars. Remember, these are your antibonding orbitals from the s and the p orbital. There are pi and pi star. Remember, that's your antibonding orbitals from the p orbitals. Since when you have a direct overlap that's stronger, the effect of raising and lowering the energy is greater for the sigma and the sigma pi's. So here we have just our S's, our two S's. That's just going to form our sigma 2s and our antibonding sigma 2s. That's what we did on the last couple slides. But how do we now throw in the p? So here are our three p orbitals, okay? The first one is going to overlap, so we form a sigma. That's our overlapping. Over here. And the antibond. The remaining two are going to form your pi. And they are the same energy. So that's why they are next to each other. They're degenerative. So you have your pi 2p, and there's two orbitals there, and then your antibonding pi 2p and two orbitals there. So if we were filling this, first you have to fill your 2s. You have to fill this and this. So that would take 4 electrons. Then you would move up here, and then you'd have to fill this orbital. And then when you're filling these, you have to follow Hund's rule. You have to have one up in each before you can double it up. Okay, but before you even get here, you have to fill all of these first. So you're going to fill low energy first. Then you have to use Hund's rule and Pauli's rule. Because here's Pauli's, 2 in each orbital spinning in opposite directions. And here was Hund's, where you had to have one up before you could double it up. Sometimes the 2s and the 2p will interact with each other. And when they do that, they actually make the sigma 2p higher energy. So here the sigma 2p came after the antibonding sigma 2s. But when they interact with each other, it makes it go higher energy. So it goes higher energy. So in that case, your pi 2p will be lower than your sigma 2p. And that's what's shown here. So here you have a large interaction between your 2s and your 2p. And when it does that, it makes the sigma 2p higher energy. So here's your sigma 2p higher energy, okay? Higher than the pi 2p. So where there are large interactions between the 2s and the 2p, the sigma 2p and the pi 2p and the sigma 2p will switch places. They switch places. Okay, when there are small or no interactions, then it follows the normal rule, where you're going to fill your sigma 2s, antibond sigma 2s, then your sigma 2p, and then your pi 2p, antibond pi 2p is sigma 2p. So notice how these two are swapped. They swap to become this when there are large interactions. Now, your molecular orbital diagram can also be used to determine whether a molecule is magnetic or not. And there are two types of magnetics. There's paramagnetic, and that's when you have unpaired electrons. Unpaired, like so on and so forth, will form paramagnetic, and they will be attracted to magnets. Then you have something called dimagnetic, where there are no unpaired. Everything is shared. So there's no unpaired, and that will give you a weak repulsion to the magnetic field. So here's the same diagram from previous, and it's asking here, predict the magnetic properties of the compound above. So which one will be paramagnetic? Remember, para means unpaired. So which one has unpaired electrons? So this one right here. See your unpaired electrons right here. And so your paramagnetic will be B2 and O2. The other type was dimagnetic. where you have all shared, or you could say no unpaired. So that would be, let's do that in a different color. Carbon, nitrogen, fluorine, neon. Because look, there are no unpaired. Okay, here you have unpaired. So your paramagnetic will be attracted to a magnet. So, if you remember from the previous slide, is oxygen paramagnetic? And the answer, or diamagnetic, the answer is it is paramagnetic. So it has unpaired electrons. So that means it will be attracted to a magnetic field. Okay, if you look here, they're pouring liquid oxygen between two magnets. Is the liquid oxygen kind of falling through these? No. The liquid oxygen is getting stuck in between these two magnets. Why? Because it's attracted to the magnetic field. So the liquid is attracted to these magnets, so it's not flowing through. It's kind of neat if you think about it. Here you're pouring a liquid, and it just stops. It doesn't flow through because they are attracted to the magnetic field. All right, this would have not been predicted by just drawing the Lewis structure. You would have no idea of being able to tell if it was paramagnetic or not. So your molecular diagrams are important in that they predict magnetic properties. Okay. Now, up until this point, we talked about diatomic molecules that all had the same atom. So those are homonuclear diatomic molecules. What happens if you have a diatomic molecule between two different elements? Okay, two different elements. How does your molecular orbital reflect this difference? So if you look here, I don't know if you notice, I'm going to circle the two S's. This is nitrogen, and this is oxygen. They are not even. In all of our other diagrams, they were always even. Oxygen is lower energy than the nitrogen. See, it's lower. Okay, so the atomic orbitals have different energies. So the interactions might change slightly. The more electronegative atom will have lower energy. So oxygen is more electronegative and it has lower energy, even for the P's. Compare the P's. See that? So that is the subtle difference between homonuclear and heteronuclear diatomic molecules. And that is the end of part 1.